Anybody familiar with the climatewisconsin.org website?
Yeah.
That's a, is everybody? Anybody not familiar with it? Wow.
I am.
Are you shaking your head as if you know you're not
Yeah.
familiar or you are? Okay, I'm going to play it anyway. So we'll,
Jesus, it would be nice not to cut that tree. But so far, to my knowledge, no person or organization or government entity has said, here, Monopoly, don't manage your force and don't provide any income from it. But so as people have economic moves, we have to start talking about management and different types of management. Taking out the bad trees, leaving the good trees, and doing that enough that eventually you'll have mostly good trees that you'll be selecting. We'll go up hundreds of years because obviously these trees take hundreds of years to take them up to their maturity. The tribes talk about seventh generation, looking out down the road to that seventh generation. So all generations will have a forest to think about like we got today. It's ancestral lands of the Menominee. Most of that land base was given up or taken, whichever your view on the historical aspect of that is. It was a lot of acres, most of Wisconsin. 234,000 acres we have today. Just about every species got an invasive disease or insect after it that is threatening its future existence. I've seen the loss of elm to the invasive Dutch elm disease that swept through the nation. And there seems to be something happening on every front and against every tree. We've got gypsy moth, we've got butternut canker. The other thing is beech scale, which isn't here yet, but it's right at the doors of either side of the forest. We're going to have to remove some of that beech to lessen the spread of that. It's doubtful, but it may save a catastrophe loss in dollars and cents. We're hoping that the forest is resilient, and it historically has been. So I think the next 20 years are more important than our last 20 years. The other part of the operation here on the mountain is the milling operations. We try to grow the trees tall, big diameter, and without too many limbs on them, because boards that are clear of knots and defect are worth more money. What we have done in maybe the last 30 years is starting to make different products from those boards, whether it's caskets or tables and that, right here on the reservation. The more we can make locally, the more that's captured here within the community, more jobs are created, more income is created. So cultural identity is everything. The maintenance of the forest has enabled the Menominee to maintain their land base, to derive income, and to maintain cultural identity.
So if you haven't been to climatewisconsin.org, I encourage you to take a look. There's a number of these videos, and I use these a lot, and I guess I'll throw the question out. A lot of you have probably seen these. It sounds like you've seen these already before, but to quiz you all, did anybody learn anything from this video? That if you haven't seen it before, or if this is the third time you see it, the first time you saw one of these videos or this video, is there anything you learned from this video? And I should have warned you ahead of time. This is the classic pedagogical mistake, right? You tell them what you're going to ask them, then you present the material, and then you ask them the question. So yeah.
But there's a certain number of invasive species that are now impacting.
Yeah. I've seen this. Yeah.
Oh, I was just going to say, I don't know if this is necessarily anything that I learned, but that definitely stood out to me is that they said that there's an invasive species threatening every species. If you look at the forest, how many species are there? And then the species threatening every single one of those is a lot of damage that can be done.
Yeah.
I thought it was interesting, or maybe I learned that they're managing a forest not just for economic gain, but also, or maybe even more so, because they want a specific forest, their traditional forest, to thrive. And so it's just a little different forestry management than what maybe I've seen or heard before, which is more, clear cutting or very broad selective cutting, mainly based on the species that will bring in the most money for timber harvest.
That's something I hadn't picked up on yet. And that actually makes me start thinking about how you would address climate change, given that specificity of management practice. So the other thing I didn't pick up, that I hadn't picked up before, I didn't realize the Dutch elm disease had swept through the nation. So there's a reason why I'm asking you that, and that is that as a climate scientist, I am totally the wrong person to say anything about forestry, right? Because I don't know the first thing about it. I couldn't name half the species that were shown in that. I can name 90% of the species that are shown in that, right? And the point I'm trying to make there is that I'm very lucky because I get to work with people who do. And it's that conversation that is critical in looking at impacts of climate change. So that's one thing I want to emphasize throughout this presentation, and kind of as we're thinking of it, and it really ties in with your GWOW model. It's not just a good idea, the GWOW model. It's when you start dealing with complex systems, you can't do the problem without that network and that communication between very different fields and looking at sources from very different sources of information. So traditional ecological knowledge, scientific information, and bringing that together and identifying where are people's priorities, what needs, how do we even define the problem in the first place? And that's where your comment I thought was really interesting. So everyone else's. Thank you all for raising your hand and not making me go through that uncomfortable silence that I do in the 101 class where I just sit and wait for someone to actually talk. But that's, if you're just managing a forest, that's one set of questions. But if you're managing a forest in a different way, that's a new set of questions. How do you manage a forest so that you get tall trees with no limbs? That's got to require a lot more time on the ground, I presume. But it may be a different set of questions that have to be addressed in order to think about the impacts of climate change. So again, this idea of that interaction with the specific individual. So I'm going to talk today, and Kathy asked me to talk about making sense of climate research, and I'll talk a little bit more about working with communities and a little bit with working in the classroom, although, again, as I said a moment ago, I'm the wrong person to talk about forestry, right? But I'm lucky because I got to work with people who do. I'm also the wrong person to talk about how you incorporate climate change into the classroom, but luckily you all can help me out with that as well. So I'm going to talk about, to begin with, I'm going to go through a presentation here of just kind of some introduction to climate research and also what it means in Wisconsin and how we've done some of the work we've done in Wisconsin. To begin with, I always start these presentations. I give a lot of talks to community groups and to sit down with people to identify these kinds of questions. What's important to you? What do you need to know? And I usually start these talks with 3 things we know about climate change. And so I'm going to start that today as well. So 3 things we know about climate change. The beginning of this is going to be very climate 101. I apologize. My goal is to try and get you all to start dozing off after lunch here. So 3 things we know about climate change. 1, global temperature is increasing. The technology for a thermometer has been around for about 400 years, and there's lots of you'll see This one is not getting argued as much anymore. It used to be that you'd say, well, you know, the temperature records are all influenced by urban heat island effect. Well, just look over the ocean. There's no urban heat island effect in the ocean, or you can get rid of the urban heat island effect. Satellite records have their own issues, correct for various things. This is not disputed, though. So global temperatures have warmed by about 1 degree Celsius in the last 100 years. 2, carbon dioxide concentration is increasing due to human activity. At the bottom of these, I'll get a PDF of this and send it out to everyone, because there's links at the bottom of these that are really useful. If you want, you can plot global temperature records for any month, any period of time at this NOAA website. So that's a nice resource. 2, carbon dioxide concentration is increasing in our atmosphere, and we know that it's due to human activity. Okay, so well, I guess I wrote it here. I was going to say, anyone know how we know it's due to human activity? This is your opportunity to really shine. Carbon isotope reference. One of the few things that we've known about climate change for about 30 years is that the carbon dioxide, that this long-term trend that we're seeing here, that long-term trend is due to human activities, due to fossil fuel combustion. And one of the sources of information that we have is carbon-13 isotopes. So I'm not a forest guy. I'm not a plant person. I was telling someone earlier, my interest is in how two fluids on a rotating sphere interact, and I could really put you to sleep on a talk of that. But so carbon-14 has a very short half-life. So it has about 5,000 years. So plants that died millions of years ago and formed fossil fuels have essentially no more carbon-14 left in them. So if we look at the amount of carbon-14 in the atmosphere relative to the amount of carbon-12, that ratio is decreasing, meaning the carbon that we're putting into the atmosphere is carbon-12, not 14. We can also look at carbon-13 records, and this is my attempt at biology. Carbon-13 tastes bad to plants, so they prefer to take in carbon-12 instead. That's as far as I know about why they prefer carbon-12 versus carbon-13. So the same thing, carbon-13 in our atmosphere, that ratio to carbon-12 is decreasing. Both of those are evidence that this is coming from fossil fuels that were once plants, and it's not coming from, say, volcanoes or biomass burning or anything like that. That's something we've known for a long time. The other thing I gotta say, this is Charles Keeling here, and this is when he started taking this data, he had about 3 years worth of records here, and these annual variations that we see is the breathing of the biosphere during wintertime, as all this plant matter is decaying. It's releasing carbon dioxide into the atmosphere, and so carbon dioxide levels increase. And then and this is northern hemisphere, this is from Mauna Loa. So then during the spring and summer, as plants start growing and taking carbon dioxide out of the atmosphere, carbon dioxide in the atmosphere decreases. And so this annual variation that we see is the breathing of the biosphere. And after 3 years, he had this really cool result that he could track this annual cycle. And then at some point, funding ran out for this, but he was encouraged to continue taking those measurements. And in doing so, going back and continuing to take those measurements, we now have the most important time series of any piece of data that we have related to climate change, the long-term variation of carbon dioxide, continuously measured at Mauna Loa. So that's a great story of perseverance. Last thing that I always say we know about climate change is that our planet is warmer because of carbon dioxide and greenhouse gases than it would be in the absence of those greenhouse gases. So we're about 18 degrees Celsius warmer than we should be. And in Wisconsin, it doesn't seem like that, but our mean temperature on our planet is about 275 Kelvin, so a couple of degrees Celsius. We should be about minus 16 Celsius. If you look at how much energy we get from the sun, that's how warm we should be. But what happens is as sunlight comes into our atmosphere, it gets absorbed at the surface, and then everything emits radiation. So all of us in the room are emitting radiation. And that energy then, that infrared radiation, gets absorbed by greenhouse gases in our atmosphere like carbon dioxide. The atmosphere absorbs some of that energy, and everything radiates, so that atmosphere radiates that energy away. The atmosphere doesn't know which direction up is, so some of it gets radiated upwards, and some of it gets radiated back down to the surface. So in addition to getting solar radiation from the sun, we also get radiation at the surface that's re-radiated back from the atmosphere. And that additional source of energy is why our planet is habitable. So you put all three of those together, and you get, we are currently enhancing that and a whole slew of other evidence. We get the statement that it is extremely likely that human influence has been the dominant cause of the observed warming since the mid-20th century. There's a whole, I'm skipping over a whole slew of addition. I mean, there's a lot of research that goes into that statement. Okay, so how do we know what's happened and what's going to happen in the future? And one way that we do this, how do we quantify climate change? We use global climate models. So that's one of the tools that I use in my research. And it turns out that if you write down the equations of how the atmosphere and the ocean and land and everything interact, you can't solve them. There's no final solution that you get where x equals 42 or whatever. So what we do is we divide the world into little boxes, and we have the boxes communicate with each other based on laws of physics. So last night, as I'm coming into the hotel, I checked the radar, and to the west of us, there was this giant system that was developing and was moving to the east, moving towards us. And so if I were a climate model, I would say, well, the box over us is going to communicate with the box upstream of us and say, there's a lot of rain, the wind is coming this direction, I'm going to say that that's coming our way. And so based on laws of physics, these boxes interact with each other, and we iterate the state of the atmosphere forward. This takes months of time on the world's fastest supercomputers until recently, until gene sequencing and so forth. Weather prediction and medical imaging were the two drivers of computational speed. So these take a lot of time to run, and the problem is that the boxes, the smaller the box, the better representation of what we have going on out there. If you look outside right now, the clouds that we have out there are pretty small. But the smaller the box, the more boxes we have, which means these are going to take a long time to run. And so we're limited by the world's fastest supercomputers in how long, in how small those boxes can be. Turns out they're about, the current generation is about 100 kilometers by 100 kilometers. So that's really big considering what could be happening inside of that space. So we take these models, we run them forward, we apply forcing associated with anthropogenic greenhouse gases or natural variation. And when we run those forward, so the black curve here is the observed temperature record, and the blue and the red curve here are two different sets of model simulations that contribute to the IPCC report, but were done as part of the World Climate Research Program. They're housed at Los Alamos, the data is. And so the red and the blue curves show what happens when we force those models with natural forcing and anthropogenic forcing. When we get rid of the anthropogenic forcing, we only use the natural forcing, we get the curve on the right here. And so we can see that statement, most of the observed warming that we've observed since 1950 is due to anthropogenic causes. This certainly supports that statement. And incidentally, if anyone has any questions or if I'm not being clear on something, fire away. Yeah?
Anthropogenic means?
It's humans. The secret ingredient is people.
Soylent Green.
Yes. Yeah. I had that wrong for the longest time. I had this slide that said, it's humans. And then my friend comes up to me and goes, you dork. It's people, not people. Okay, so anyway, this discrepancy is... So looking forward, what's going to happen in the next, say, 100 years? And so the way we do this is we come up with storylines of how our global economy will evolve over the next 100 years. And whatever uncertainty there may be in the science of climate change and whatnot, it is far more constrained than uncertainty in the stock market and global economy. So we don't know what's going to happen in the future, so we come up with these storylines. So these four different storylines, They're now referred to as these radiative concentration pathways. But essentially, what I'm showing it will be similar to this. So this red curve here is a business as usual scenario where no one gets along, no one shares technology. We rely on fossil fuels for a long time. Global population maxes out later on in the century and so forth. This blue curve here, on the other hand, is one where we rapidly mitigate, where there's a lot of sharing of technology. We rapidly move away from a fossil fuel-based economy. Global population peaks out in the next, say, decade or so, and so forth. And then in between are these other scenarios. So you can see by the end of the century, we have two very different results. And the actual amount of temperature change, of global temperature change from these two, I think is less different than the slope of the curves. This curve has leveled out. This red curve is still accelerating, right? So these are very different scenarios out 500 years. This red curve comes out to about 12 degrees of global warming, Celsius of global warming. Locally, that's just, I have no idea what that would be. Yeah?
What would that be Fahrenheit for those of us who are math challenged?
I always have to see, I'm with you on that. So 1 to 1.5 degrees by the end of the century is about 2 degrees Fahrenheit, or by mid-century is 2 degrees Fahrenheit, and then 1.5 to 7 degrees Fahrenheit. By the end of the century, 12 degrees is about 20 degrees Fahrenheit, I think. Am I doing the math right on that? 9/5 period of 1. That's one of the things. I can do kilometers, I can do kilograms, but I live in a Fahrenheit world. So, okay, so by mid-century, in the next 40 years or so, it doesn't matter what scenario we're on. Whatever we do now, we're going to see that warming, right? Even this scenario here, a lot of people look at these and they tend to gravitate towards the one they want to see. All of these are equally likely, and I will say that right now we are above every one of these scenarios in terms of our emissions and the rate at which our emissions are increasing. So, in Europe, everyone talks about this as being the realistic scenario, the 4.5, and that if we're really ambitious, we'll get to this. In the U.S., scientists talk about this one as being the realistic scenario, and if we're really ambitious, we'll get down to the 4.5 scenario. So this brings up two things about what we can do about climate change. You'll hear people talk about mitigation and adaptation. And mitigation is some steps that we can take to avoid some dangerous amount of climate change, so to reduce the amount of climate change that we expect. But even if we do that, even if we are able to get down to a 4.5 scenario, or even a 2.5, if we look at where we're coming from here, there still is an inevitable amount of climate change that's going to happen. And so we need to be prepared for adaptation as well. So one of the messages in this is that oftentimes we hear about stopping climate change, and even if you were to shut a light switch off in the global economy right now, we would still see about the same amount of climate change that we've observed in the last 100 years, just because of the time it takes for the climate system to respond. So we'd still see about a degree Celsius worth of warming, even in that scenario. And so we need to be prepared for that in some way. This brings up this brings up the point. The point I'm trying to make is that in addition to mitigation, adaptation is something that is now seen as an important action. Okay, so that sounds doom and gloom, but really there are opportunities here, and so I want to talk about. I don't want to sound doom and gloom. So if you're like me, you see global temperature will increase by 1 to 4 degrees Celsius by the end of the century, and it means nothing to you. So I had a guy come into my office. He builds augers. He works for a company that builds augers for really thick lake ice. And he comes into my office and he says, I got to know if the last few years are going to be the norm in the future. And this is before I kind of got started with WICCI. And my reply was, well, global temperature will increase by 1 to 4 degrees Celsius over the next 100 years. Which is, the guy leaves my office like, this guy's useless, right? And it points out, again, the point that there needs to be that communication. I don't know what's important to that person. How big are his augers? How thick does the lake ice need to be? Because if it's thin lake ice, someone will buy a smaller auger and his company's out of business, right? So how thick does it need to be? Where's his range? Right? There's all of these parts of the puzzle that when you're dealing with adaptation, that communication is necessary. So our experience is local, and so the effort we put together in Wisconsin as a whole is the Wisconsin Initiative on Climate Change Impacts, and this deals with adaptation in the state. So when we first put this together, this is under the Doyle administration it was put together when Doyle was in office, and Doyle had an effort to look at mitigation of climate change at the time. We didn't want to step on toes, so as we put this together, we said we're only dealing with adaptation. Administration changes, and now mitigation is totally off the table, but adaptation is still fine. Everyone is still sort of solidly behind it, although not in the last few months, but we'll sort of deal with that later. But with this was a partnership initially between the university system and the DNR, and it is interesting. You go into either a office of a Democrat versus a Republican, and the response you get is very polar until you say, we're dealing with how this affects your constituents. And then people generally get behind it. That's kind of an important reality. If you're dealing with a politically charged environment, adaptation is a lot simpler as an approach. And starting from this GWOW model where you don't even start with climate change, you start with what's important to you, and then go from there. That's a much easier approach in terms of gaining traction. All right, so one of the first things that we identified, we talked throughout WICCI, and they identified a need for local scale climate data. So this was at the time typical resolution of the climate model. You can see that Wisconsin is covered by, say, 2 grid boxes, and if you look outside any day, you realize that's pretty coarse resolution. And so downscaling is the act of producing local scale information based on the information you have at the large scale. Now, in doing that, if you want to get into information theory, you're adding information which isn't there in the first place. And so any one of these things is just what could happen, right? Ideally, you have enough realizations that you do this in a way that you kind of expand the range of possibilities of what could happen. We're not forecasting what's going to happen July 27th, 2054, right? But what is produced on that day should be representative of the kinds of conditions that we might be able to expect then. This is the one slide I have to put in here. This is the technical slide, sorry. And yeah. So when we did this, we submitted a proposal to the Wisconsin Focus on Energy program to come up with this downscaled product. And then the deadline came, submitted the proposal, and then we had all these conversations in WICCI about what do people actually need. And they came up with all these criteria of what they needed. We got the grant to produce this downscale information. We started the project. It was a morning in September. We had a 9 a.m. meeting. I remember that specifically because by 9:15 we realized that our entire methodology that we had proposed would not meet the needs of the people who were going to use the data. And we scrapped the entire methodology 15 minutes into the project and came up with a new methodology that would meet the needs. So let me give you an example of why methodology matters here. If I just take stations around Wisconsin, you can tell where the stations are here. I'll explain why in a minute. And I just interpolate and come up with the mean temperature in Wisconsin in July. I get this map here. And it's kind of splotchy. I look at that and I say, no, it's being influenced by outliers, but at least it's kind of smooth. This is precipitation, not temperature, I'm sorry. On the other hand, if I look at the fraction of wet days, so if I want to go on a picnic in Wisconsin, what this tells me is I should go find a weather station because my chance of getting wet is lowest if I'm sitting right underneath the weather station, right? On the other hand, this is the extreme rainfall amount. If I don't want to get really, really wet, I should go as far away from a weather station as possible because that tells me that I won't get, that the extreme rainfall will be muted in those areas. This is all because of the interpolation methodology. If it's wet here, but it's dry here, if I just interpolate, it's wet everywhere in between, right? If it's the chance of having a really extreme rainfall here and a really extreme rainfall over here is really low, right? Rainfall, I mean, it pours in a location, right? And so if I have an extreme rainfall here, it'll almost always be muted somewhere else. And so I don't get the extremes as a result because I'm interpolating. So we had to design a new methodology that would allow us to look at things like extreme rainfall. And that's what we did. So this is all available from the this website, which I'll put up a couple more times, and we'll pass out as PDFs or something later on, where you go and you can look at the historical record.